Our next talk in the Northwest Database Society series. Today is my great pleasure to introduce Professor Stratos Idreos. Stratos is a professor at Harvard. He received his PhD in Amsterdam. He received the ACM Sigmod Best Dissertation Award for his PhD on database cracking, a fun technique that took the database community by storm. Since then, he became a professor at Harvard. He visited many other places. He visited the PFL, Microsoft, the IBM Alma, and Trento, Singapore, and he's at Washington. And he writes beautiful papers on fundamental and very contemporary techniques for organizing data and database systems. One paper I really like is his paper on LSM trees, on LSM indexes from last year's Sigmod. So today, Stratos is going to talk about the data calculator.
Thank you, Dan, and thanks for having me here. I'm going to talk about the data calculator, which is, I see the data calculator kind of like the umbrella of many things that we do, and maybe if you've seen some of our papers, you'll connect it as well. So really, long term, what we're trying to do, we're trying to figure out if there's a way to reason about the design space of data structures, okay? I'm not going to try to sort of motivate data structures a lot. They're really fundamental. They're everywhere. Anything we do depends on data structures. But I would still like to highlight that the way things are going, it's not only that we have to design an algorithm by taking data structure decisions first, but also performance really depends on data structures, okay? And that's because of the way hardware has evolved over the last few years. And there's this other little thing that makes this problem really challenging and interesting, and also it's not going to go away anytime soon. And that's the fact that there's no really perfect data structure. Okay, so anytime we design anything, what we are making effectively is a compromise. And it's a compromise between the read amplification, update amplification, and memory amplification, and in the future also likely privacy and adaptivity and other things. Okay, and because hardware and applications are changing all the time, we really have to rethink about data structures all the time. Okay, so again, reasoning about data structures. What does this mean? So in some ways, this is really a vision from the 70s. Many people have argued that, okay, we should be understanding this space a lot more. What we are doing here, we're trying to think if there's like a few concrete questions that we can go after. And here's the two questions that for now we think they're important. And the first one is there some way that we can actually sort of know all possible data structures that we may ever invent? Okay, and that might sound a bit too much, but that's the design space part. Okay, so knowing what's the possible design space for data structures. And now if we have that, the next question is, will we be able somehow to reason about any part of this design space? So being able to pick any design and somehow say something about its performance. Okay, so that's the compute performance part. So I'm going to try and make this a bit more clear. So this is what I think is the sort of minimum engine that we should have to enable reasoning. So this thing would take, and that's the data calculator thing, it would take three things as input. The first one is a high-level specification of the layout of a data structure, so how you put data. And then a high-level specification of the workload and the hardware. Okay, so that's the three inputs. And then automatically, by itself, it computes what? It computes the algorithms that this data structure should implement to support specific key value store, effectively, API. And then it also computes the cost. And that's the cost that you would get if you were to implement these algorithms for this data structure and test the particular workload and the particular hardware. Okay, and all of that should happen without the user. And a user can be an algorithm or a researcher or a scientist, whatever, without anybody doing any coding or even having access to the hardware. Okay, so that's what this engine should do. That's the dream. And then what we're saying is that when we have that, then we can go after all the other more high-level things that we would really like to do, and that would enable reasoning. And I'm going to tell you a little bit about each one of them towards the end of the presentation. Okay, so I'm going to tell you about design space, cost synthesis, and a little bit about how we can use this thing. So design space is really thinking, how do we store the data? Okay, then a data structure would have a potential an optional index, and the index could be some kind of metadata, filter, model, function. Okay? And then also, how do we implement the algorithms? So this is really thinking about the design space. It's thinking about all those questions, okay, and trying to figure out if there's a pattern there. So thinking about this problem, there's three kind of realizations that I would like to share, and that's what drives our research. So the first thing is this kind of realization that any kind of design, it can really be expressed as a set of concepts, okay? And this is really all the decisions that we've made when we came up with a particular data structure. Now, starting from that, we can go to the first thing, which is more like a conjecture, but it's a reasonable conjecture. And that's that any kind of design is really one of three things. It is a combination of existing concepts, design concepts, a tuning of existing design concepts, and in some cases, it can also contain some radically new design concept that we see for the first time. And then the third thing is that by now, we've done so much research that we've discovered many of the fundamental design concepts by publishing all these data structures, and most of what we do can actually be classified in the first two categories. So it's either a combination or a tuning of existing design concepts. Okay? And that's really what leads us to our motivation and the methodology, which is, let's take a step back and think about the design space now, as opposed to thinking individual data structures, and try to see if there's patterns in the design space. Okay? I'm going to make an analogy, which is kind of a loose analogy, but it will make a little bit more clear what is the methodology we're trying to follow. This is Dmitry Mendeleev from 100 years ago, and that's a periodic table of elements. And what they did really is they organized existing elements, and we had the structure of them. We could classify them based on their properties and some of their components. And that was great because we could explain some things about the existing elements. But the most wonderful thing was that for 100 years later, people would actually go and do research purely triggered by the structure of the periodic table. So they would see a gap in the periodic table. They would say, well, an element might exist, and it would have these properties. Let's go and do research for a few years and figure out if an element is there, right? And I think as of recent, the periodic table is kind of full, and this is one of the latest. It's called Meconium that was discovered. Okay, so this is really a methodology, and it even starts from ancient Greece and Leibniz in the 1600s. In computer science, and in our field specifically, Mike Franklin, in his PhD, it's one of the favorite examples. He actually did research on transactional cache consistency maintenance algorithms, which is something very, very, very complex. And what he did is that he figured out the basic components of those algorithms. He classified the algorithms in a design space, and that allowed us to understand existing algorithms, but also see possible algorithms that actually are generated as combinations of those components, and even say stuff about their potential properties. Okay? So this is really what we want to do here, follow this methodology. So we want to figure out, is there like a small set of design principles that create all data structures possible? So we're going to go out and figure out these principles and then study the design space and see what the structures, what stories this structure tells us. Okay, so that's great, perfect. How do we do that, right? This is kind of a hard problem, and there's no great methodology. It's a trial and error thing, okay? And even I verified with Mike Franklin that it was a trial and error thing for him as well. And the periodic table, if you read a bit of the history, actually we had tens of periodic tables over time, and just the last one was the one that stuck. So the kind of methodology that we kind of follow is that a first principle for us, for data structures, is really a design concept that you can't break any further. It doesn't make sense to break any further. So for example, let's say you have two nodes in a data structure. Do you link them with a pointer or not? Like that's a binary decision. You either do it or you don't do it. Okay? So that's a first primitive. So we separate, one decision that we made early is to separate layout from access. So layout from access algorithms. And that's because they're really huge different design spaces. And when you decide the layout, you actually drive the decisions at the algorithm side. So then the two steps that we follow is that we take big classes of existing data structures. We try to break them down into the first principles, see if those first principles generalize for other data structures. And then actually the third step, which is quite crucial, is that we try to answer open questions in our field by stress testing this design space and stress testing these primitives. And sometimes some primitives prove that they're not primitives and we can optimize them away, and sometimes we figure out even more primitives. So I won't tell you, I don't have time to tell you a lot about this process itself, it's actually quite interesting. This is some of the areas where we're going after, and this range from studying plane arrays to studying neural networks, because data structures are really everywhere. And by stress testing this and figuring the design space, there's many things that we can do, ranging from, and this is really diverse spaces, such as optimizing NoSQL key-value stores and make them a few orders of magnitude faster, figuring out fundamental stuff about access path selection in relational systems, and that we've been doing it wrong for a few decades now, all the way to optimizing neural network access. Okay, here's the first concrete model that we actually have out, and we sort of know it's correct. So this is a set of principles. It covers bulk loading and bulk loading operations and point and range queries. And what you can do with this, and I'll show you examples of some of them, is that you can describe blocks of data as sets of concepts. Okay? So let's see some examples so we can see some details. So imagine now we have a big data structure and we're describing blocks of data. So this data structure holds keys and values. Okay, it's a key value store. So you could say this block of data doesn't contain keys, doesn't contain values, right? So for example, for a B+3, the internal nodes, they wouldn't have any keys or values, but the leaves, they would have keys and values. Okay? And if you do have keys or values, how do you store them exactly, physically? So are they stored as key value pairs, or are they stored as a separate array for the keys, a separate array for the values? These are two totally different design decisions. Then this block of data, does it create some kind of partitioning for the domain? Maybe range partitioning, temporal partitioning, some kind of weird function, and so on. If there is partitioning, then you start creating subblocks within the original block. Then those subblocks, how do you access them? Do you have direct access? Do you have pointers? The subblocks themselves, are they connected somehow with immediate links, with skip links, and you start creating a skip list? You might have some kind of filters because you have all the subblocks and you would like to filter each subblock and not go in. So maybe you have Bloom filters, maybe you have zone maps, like you do in the LSM trees. And if you do have those filters, do you store them scattered in the subblocks, or they're actually consolidated in a single area of the original block so you can search them fast enough? Or the subblocks, are they outside the original block or they're inside? If they're outside, you start creating a hierarchy, and that starts looking like a full data structure. If they're outside, though, are they stored scattered in memory, like in the typical children of a B+3, or they are stored in a consolidated area in memory, like in the cache-conscious B+3? Okay? So this is the kind of detail that you have to go down to figure out these first principles. And what we do with those things is that each time we describe a set of them, and each time we do that, we describe a block of data out of the possible space of all blocks of data that we can describe from these principles. And then if we put many of those blocks together, not in terms of the same blocks, but different specifications of a block, we start describing full data structures. And most data structures that we actually publish in the literature, they are 2-node structures, and some they are 3. And these are, for example, some of the sort of state-of-the-art data structures that we can already describe. Okay, so perfect. So what can we do with this thing? So the first thing that we like to do is create our own periodic table. So that's the periodic table of data structures, or eventually it will be. So what you have here is you have different classes of design primitives. Vertically, horizontally, you have different classes of data structures. And wherever you see done in a cell, it means that there's at least one paper that we know of that somebody has published applying these design primitives in this class of data structures. And already, this is a zoomed out version of our principal design space. And already, you look at it and you're like, oh, it's almost empty, right? After 50 years. We've done a lot of work with B+3s and not so much work with other things. And we can start having all sorts of interesting observations and discussions with this thing, and we can even give here hints about what would happen to the read, update, and memory amplification should you were to implement a particular design principle in a particular class of data structures. So you can also start using this as kind of a hint on where you should drive your research or your design. Okay? So I want to tell you more about the low-level observations here. But if you think long-term, what would we like to do? We would like to automatically design data structures. We would like to automatically detect bad designs in existing systems. We'd like to automatically figure out the best hardware to run our workloads. And like challenging stuff like that, right? And automatically or semi-automatically, that would also be fine. So what is the problem? The problem is that we just generated this massive design space that is combinatorial, and already with this first model, we have more possible data structures than stars in the sky. Okay? So specifically, the numbers are that we can create 10 to the 32 two-node structures, which is a lot. Okay? So we cannot just manually go and figure out stuff here. We need something more. And here's what we think that we need. So if that's a design space and you have arbitrary points, and each point is a data structure, the minimum functionality that would enable us to do interesting things is being able to pick an arbitrary point in the design space and compute its cost. Because if we can do that, then we can compare two points and we can start designing algorithms that traverse this design space. Okay, so that's what we're focusing next. So that's the cost synthesis part. So what are we doing here? When we design a data structure, normally, like a single instance of a data structure, how do we judge it? We do complexity analysis, right? And that tells us how things might scale as we add, let's say, more data. If we want the ground truth for a particular instance of a data structure, implementation and testing on particular data and hardware tells us the ground truth. And there's a third approach, which is called generalized models. This is a bit of a lesser-known approach, but people have been doing this since the 70s. And the idea is that you create these very elaborate models that do take into account hardware properties. Okay? People have been doing this both for disk and tape and lately also for memory. Now, the thing is that those things are hard. Ground truth in terms of implementing something and testing is really hard. Doing the models, you would think it's simpler, but it's actually harder. So we've been trying for the last several years in my lab several of those things and creating these very elaborate models and doing all those things. Here's, for example, our models from when we tried to revisit the access path selection problem in database systems. And we've showed some very interesting new results that it happens in a suboptimal way and all that stuff. But you look at the model now, at least I look at the model now, and I'm not sure exactly what it does. And the moment you change the hardware or the algorithms a little bit, you really have to go in and redo the whole thing from scratch. Okay? So that's not a good approach to do this for arbitrary points in a large design space. So we need something else. And what we need is really we need to be able to just pick a point and automatically do this thing, automatically figure out the algorithms and say stuff about the cost without so much human effort. Okay, so that leads us to the synthesis part. Okay, so one approach would be that we look at the specification of a data structure that we picked, and then we write a set of rules, and the rules tells us how what the algorithm should be, or tells us stuff about the cost. Okay, so let's see. So you could say I have the specification of a data structure. It tells me that this part of my data is sorted. So I could put this rule here that says you should have an algorithm, let's say for a get operation that does a binary search here, or some kind of sorted search. Okay. So the problem is that this rule would be correct, but then exactly what sorted search you would do? You would have different kinds of algorithms, and even for its algorithm, you could have different kinds of low-level implementations that would make a substantial difference in performance for different hardware as well. Okay. So, and one approach would be that we go in and we write rules for all those things, and then we would never finish, right? So what we do is we do something that is a little bit of a hybrid among all these existing approaches. And what we do is that we start, again, we figure out a small set of fundamental access patterns that would comprise full algorithms on a data structure. So for example, let's say we just said sorted search. A specific implementation of a binary search algorithm would be such a low-level access pattern. And then we have a little bit of code that describes exactly this algorithm. And then we train this code on a particular hardware, and we learn a model. Okay? And what has happened by doing that is that, well, without really doing any more effort in terms of human labor, we can actually capture all the things that we wanted to capture in our very elaborate models, which is the algorithmic properties, the hardware properties, and all the engineering properties here. Okay, so that's the intuition here. And what we end up having, we have this hybrid of rules that tells us big patterns for our algorithms, like data is sorted, do a sorted search, but the algorithm and the engineering is decided by the model. So then this calculator thing, it computes costs in the following way. There's a training phase where for a particular workload, we would go in and we would train all our basic access patterns. And basic access patterns are things like scan, random access, a Bloom filter probe, a binary search, and stuff like that. And then we learn a set of models for a particular hardware. Okay? So then you can have a human engineer, a researcher, or an algorithm inserting high-level specifications of a particular data structure and the workload. Okay? And so then this thing will actually go step by step through this workload. And for each operation in the workload, it will reconstruct the state of the data structure. It will figure out the path that it's to follow. And for each node in the path, it will pull out its specification. And based on the rules and the models, it will decide the algorithm. And then it will, based on the models, it will compute the cost. Okay, so based on the rules, it will figure out the rough sketch of the algorithm. And based on the models, it will really fine-tune the algorithm, and it will compute the cost. And by doing that, operation after operation, you can compute the whole cost for the whole workload, and by aggregating everything together. Okay, how do we judge this thing? We want to judge calculations versus what you would get from an exact implementation testing on a real hardware and data. So here's some numbers on B+3. So black is for the calculator, gray is for the actual implementation. And you see that overall we're doing pretty well. We're getting really close estimations here. And we're also capturing caching effects. So this is on the x-axis we increase skew, and skew would create caching effects, and we're also capturing that part as well. And if we try the same thing for cache-conscious B+3, which is basically a B+3 where the nodes are consolidated, the children are consolidated, which is better for each, we capture the effect that this is much better than the B+3, and also the fact that it will improve less with skew because it's already cache-conscious. Okay, and we have results with other sort of well-known class of data structures ranging from tries to hash tables and other stuff like that. Okay, so we can, for some class of data structures, we can accurately estimate costs. Now, what do we do with that? Okay, so the analogy here with the calculator is the following. So in the same way that people use the normal arithmetic calculator thing in everything, they can use this thing in everything that contains data and want to build algorithms on top. So here's a few examples. The first one is what-if design. Okay, so the idea here is this thing takes three things as input. If you start varying those three inputs, you already can have quick insights on important things. So for example, you can keep fixed the workload and the hardware, and you can try two different specifications of a data structure. And then just in a few seconds, you can realize whether you're going to implement this new feature in your system or not by seeing the difference in performance. Okay? Or you can keep the design fixed and the hardware fixed, and you can try two different workloads because you're thinking maybe of introducing this new feature in your application that would change the workload. And again, you can see what the impact would be. Or, of course, you can keep everything else fixed and change the hardware, and you can decide if you want to buy new hardware or if you want to place this query in a specific machine and so on. And all of that happens in our current experiments in about 20 seconds in a normal machine, and there's opportunities to optimize this down a lot. So that's what-if design. One thing that I'm really excited about is what we call design continuums, and that comes from observations of the design space itself. And this is where I think studying the design space, it can really bring new kinds of insights. So what we're doing with design continuums is we're trying to unify classes of data structures that we normally think them as different, but actually they can be described from the same unifying theory underneath. Okay? So you can think of sorted array and log as two extremes, even though they're not really, but conceptually they are extremes of some design space. This is very read optimized, this is very write optimized. Okay? And we've already shown that actually LSM tree is part of this design space, and you can tune it anywhere between a log and a sorted array and all sorts of intermediate phases, so you can manage read-write ratios just by playing with a few of its design primitives. And some of our latest results indicate that you can actually create this whole unified theory that includes also B+3, or actually any kind of B tree variation in there as well. And if you think about it, a B tree is actually just an LSM tree where you haven't really pushed everything down yet, and you can you keep track by keeping the fence pointers around. Okay, and the last part, of course, is automatic design of data structures, which has been a dream forever. Give me a workload, give me a hardware, and I'll design the best thing for you. So here's a toy data structure that the thing designed by itself. So basically, you give it a workload, and the hardware, and starts designing weird things that they don't really exist in the literature. And this is actually our own way of describing data structures. So each one of those things it's a graphical representation of sets of primitives, and we're describing its radiuses. And then, so this thing combines basically range partitioning and hash partitioning and logging in one data structure. And it took it about half an hour to generate it for some small amount of data. Okay, but already we have results where with dynamic programming or with genetic algorithms and reinforcement learning, we can start generating weird new data structures as combinations of the existing components. Okay, so there's a ton of related work on data structures. There's 4 people that have really sort of affected some of the methodology that we do. Esping Yao, he was doing a lot of research in the 70s in that field. He was, I think, one of the first ones, or even the first one, who was thinking about storage advisors. Don Battery has done a ton of work on modular and synthesis of data systems, or systems in general in engineering, but he was also, I think, the first one that played with languages for data structures. Joe Hellerstein has done all this extensible, wonderful indexing stuff, and Stefan Mannekol has done the generalized models for in-memory systems. And as I said, one way or the other, this has been a dream from the beginning. One of the nicest ways to put it, Robert Azan had this paper in, I think, 1976 or 7, where he had these 5 challenges for the future, and one of them was coming up with a calculus for data structures, and I think of our work as a small step in this direction. Okay, so there's a ton of future work, as you may imagine, ranging from thinking about the design space itself and expanding the design space, making it, in general, like figuring observations and so on, all the way to building algorithms on top of it, and of course the infrastructure of the calculator itself, and making it fast and easy to optimize, and so on and so forth. And I will leave those things here and show you also the faces of my students that do the hard work. And thanks for listening.
Time for questions.
Yeah, it sounds like, I just want to get clarification here, that you've restricted yourself to a domain of databases.
No.
Okay, so I could design data structures for my sparse linear algebra algorithms, my finite element codes.
Ideally, in the future, yes. So we did. So what the model that I showed you is actually a key value model. It doesn't have to do with databases. People think I'm a database person.
Well, still in the data side, the key value still is data, but the database is the wrong word.
Right. So I will use the word data.
Still in the data management.
I will use the word data system. But anyway,
Okay, sure.
so people would say that something is not a database until it have, I don't know, 5 different data structures inside, and a key value store doesn't do that.
Fair enough.
But yeah, so I think, and also I think for the database community, our work should be more about servicing storage and not relational algebra. And so I think data structures are really fundamental, and everybody has data structure problems, and so we can service that. So yeah, so I think as long as we can describe a workload and a target hardware for an application, then we can figure out a data structure. So as long as you can describe your workload as put, get operations, or select range, or update something, which is the more fundamental data access patterns, then we can start from there. Yeah. So we don't have any database specific restrictions here in any way. Yeah.
So my question is, so if I build a system, I will typically have maybe many data structures, and then design decisions for one data structure will then affect design decisions for the other data structure, right? So maybe I just missed it, but how do you manage this kind of interactions between these design choices for different data structures?
Yeah. So okay, so I think maybe if I slightly rephrase that, so let's say we could have the same data represented in different forms, and we can take this into account in how we make these choices. So right now, everything that we've done assumes a single copy of data, and so it would be a single path for your data, and that would be the optimal. But once you actually allow memory amplification, and so you would allow more than one copy of the data, or any kind of hybrid in between, you can start making those choices. So I think, even though that's not a trivial problem in any way, I think this is one of the most trivial problems in that space that you could actually solve, in the sense that it becomes part of the search algorithm. So the search algorithm could say, okay, I have some storage budget, I can put more stuff in here. And then you compute the costs, right? There's other things that you might want to make as as a restriction or a core restriction of the space that might be harder, such as privacy, for example.
That's true, but actually my question was slightly different. Like imagine I don't have only a key value store. What I have is maybe a query plan, and in that query plan I have a join and another join and an aggregate. So then in the join I want to have some state to compute, right? And then I have another one. So then if I start to change the data structures here, maybe to use more memory and be more optimal, then the next operator will be affected by having maybe fewer resources, or the data will run differently.
That's definitely more complex. Now we're going to query optimization, I think.
But any system that I have, if I need more than, so it could be that it's the same maybe data set, or maybe you have different data sets taken off. Maybe it's just competing for resources.
No, so I wouldn't know off the top of my head how to solve this right now in the same framework. But again, I would imagine that this becomes a high-level algorithm that can use this infrastructure, because you can build an algorithm like now you build optimization methods by querying the optimizer, right? So you could query this thing and say, okay, what if I do my scans with these 15 different data structures and just query that space, right? And then you would have this option to play with these different data structures at least and start thinking about the high-level algorithm. So I think this high-level algorithm is likely something more complex, but it can use this infrastructure. But yeah, I see where you're going, and the original motivation for this was, we're calling this self-designing systems, that we would start designing systems themselves as opposed to just data structures. And after a year, we gave up because it's a much more complex problem. So we thought we would focus here and actually do something. Yeah.
Great talk.
Thank you.
Once you find a data structure that can be sort of get arbitrarily complex, because that might be what the cost synthesis tells you what it should be. So is there a notion of like regularization you want here, where you're sort of balancing performance with some notion of simplicity of the data structure, and so you're willing to sacrifice a little bit of performance because you don't want to have hash indexes hanging off of BJ's, hanging off of this, hanging off of this, in order for either communicability to programmers or some other kind of
reliability,
robustness. It's maybe a sensitivity analysis. The other thing is like, well, this is the right thing for this workload, but if you change it slightly, all of a sudden the role, if you have to change it completely, that's probably an undesirable property. Can you factor that into this framework?
Not now, but you could. And it's kind of I think, a next step in terms of the search algorithm optimization problem. So, the first thing that I would try is just add some noise in the workload and so on, like the typical thing that you would do. And then we can go from there, and the standard things that we can try. But and I'm not sure if it's more complex than other incarnations of this problem, but maybe it is, maybe it's not. The other thing that you mentioned for the maintainability, I think that's an exciting thing. And what I'm going to say, it's not my idea. Someone in the industry sort of had this idea when I was sort of presenting this thing, and they said, I don't want you to give me the most optimal data structure. Give me the 10 best data structures, because the second one might be way easier to implement, right? Or much closer to my design that I have now, and I might choose this one. And this kind of at least in the beginning, just showing those things, and maybe in the future even ranking them somehow, sounds like a wonderful path forward. Yeah.
Yeah, that's standard in like the ranking, stochastic ranking and selection literature, right? You want there's these notion of multiple comparisons with the best that kind of isolate a set of your top performers and actually estimate the differences in performance.
Yeah.
So that might be relevant.
Yeah, thanks. Yeah.
So, what's the status of this? Is it in a form where someone like an idiot like me could grab it and try and use it with my favorite workload? And
so if you don't mind a few bugs or a lot of bugs, yes. So there's even so it's research software, and there's even a graphical interface that you can actually graphically design this kind of boxes, and it actually computes costs and stuff like this. And we're actually refactoring and aiming to have something open source pretty soon. There's a key value store aspect. So this Crimson DB system that we're building, where we're like more seriously trying to push out something very soon, and that's because we're having the specialization on NoSQL key value stores just so that we can build a complete system sooner, and because it's a space that is way more restricted. So that's something that ranges between arrays, LSM trees, and B trees. So if that's more your target space, we'll actually have something way sooner than that. Yeah.
So you showed the slide earlier where you have the data calculator in the middle, and there's sort of three inputs. So there's the design of the data structure, the workload, and the sort of hardware. You showed us what the design space looks like, but how do you characterize the workload in the hardware for this tool?
Yeah.
Great question. So, and I think I maybe even introduced this in the wrong way because I said high-level specification of the workload and the hardware, and that might. So the workload we actually right now we get it in an exact way. So we would get a series of point queries, range queries or bulk loading operations. So basically that's the exact workload. And you could think of future steps, and some people are working on this in our community, characterizing a workload statistically and doing something with that and so on. But that's what we get as input now. And for the hardware, what we actually have, remember this slide where I showed you how we train? We train on an existing hardware. The hardware specification is not really, the word specification was wrong. It's actually, here's the hardware, and I've trained on this hardware and on this exact hardware. And so in the end, what you end up having is I have this 100 different kinds of machines that I've trained, and that's my list of hardware. So it's not at the detail where maybe you want to have it in the future, where this is the CPU and this is the memory, and then you can start also designing hardware using that. We're not at this level.
Okay, so does the workload have any notion of what data is in the store, or just the queries that we issue against?
No, it has, because it has the bulk loading operations.
Okay.
Right. So you give it a sample of the data that you, and that's how you create the state, because the state really depends on. It's not just by the specification. The state really reconstructs. It doesn't build the data structure that would be very, very slow. It reconstructs the state in the sense that it says, I'm going to have 1,500 nodes. It's going to have 100 elements, 8 byte each, and that's the kind of information that we have. And to have that, we need to know exactly how much data you get in. Yeah.
So I was wondering, I get this question a lot, and now I'm going to pass it on to you. So how you talked about design principles, right? Being like kind of atomic, like you can't break them down. But then the design principles that you had was still like a bit compromising on that, right? You say a binary search is a design principle, which seems to make sense in this context. But how do you know this is as low level as you want to go, right?
Okay, so I think this is so. When you start discussing about the design space, you can go crazy. That's my okay. Now, so the decision that we've made is that we separated layout with algorithms, and there's a very specific reason, and here it is. I think the layout we can actually decide, and it's a hard, but it's going to be a fixed design space. And these are not, sometimes they're binary, sometimes they're a function. The algorithms, though, what happens is that, and that was the intuition, and that's why I went this way, is that the algorithms are going to keep expanding. So, for example, always, every year, someone will come up with a new implementation of binary sets because they're going to use these new SIMD instructions by Intel or whatever. And what we have now is that all you have to do is just put this 50 line of code in your system. In this system, it will learn the model, and that becomes part of the library immediately without doing anything else. You just make it part of the sorted search library. And then, let's say you are doing this so you can try it in your own B+3 where you have sorted leaves. But anybody in the group that has in their data structure any kind of sorted block of data, like a hash table with sorted buckets, immediately the system would search and consider this algorithm now for any kind of data structure, right? And that's extensibility. So it's not only easier to put this in the system, it's also extensibility.
Right. But it works in this direction. But if you want to propose new searching algorithms, right? Like it would not.
Right. So if you want to propose new fundamental access patterns, like the sorted search or the random probe and so on, that's the research that we can do to expand the design space of access patterns, right? And then what you have to do is you have to make it really part of the system, and that's a research problem, because you have to figure out also the rules or what kind of access patterns are incompatible with each other and stuff like that.
So I just want to make sure I understand. Your system does not invent new algorithms. Your system invents new data structures? So you as
both.
You will invent new algorithms?
It invents both new algorithms and data structures. New algorithms in the sense of new access algorithms in data structures, right? So you put algorithm and you get algorithm and so on. But it depends what you mean by new algorithm. So if you remember the slide where I showed you everything, most of what we do is a combination or a tuning of existing design concepts, and we publish those things. So these things it can do. It cannot invent a new concept that doesn't exist already, right? It can combine existing concepts, both in the layout and in the algorithms.
Yes, we are running out of time.
Thanks everyone.